Hey guys, welcome to the mean value theorem and Rolle's theorem, which are basically the same theorem. But we're going to talk about just how we kind of use this theorem and what it tells us. And the mean value theorem, often abbreviated MVT, states that if f of x is continuous on a closed interval, you see there's the brackets around AB, which indicate that it's closed, and differentiable on an open interval. You can see the parentheses indicate that I don't count the endpoints. There's at least one value of C. This is an X value. There's some X value in here so that the derivative at that value is equal to f of B minus f of A over B minus A. And this expression here, f of B minus f of A over B minus A, is the slope between A and B. And this picture here on the next page kind of makes that a little clearer. Like here's A and here's B. And so there's like this point here. This is f of this y coordinate. Let me redraw that. If this function is called f of x and this is A, then right there, this y coordinate is f of A. And if this is B, then this y coordinate, if you go across to here, is f of B. And so you kind of have these 2 points here, A comma f of A, and this is B comma f of B. And the slope between these 2 points is y2 minus y1 over x2 minus x1, which is f of B minus f of A over B minus A. So this is a slope between 2 endpoints of some piece of a function. And what the mean value theorem says is it says that the derivative of f is going to be equal to this slope somewhere between A and B. So you can see that you could draw the slope here. It's drawn at this kind of thick arrow between A and B. And you can see that right here, like this is some value between A and B, that the tangent line is parallel to that. Parallel, which means same slope. That's the worst writing of the word parallel in history. I'm going to rewrite that. Parallel implies same slope. So like this is like a slope between 2 points. And this is like the slope at a point. But these are both a slope, and the mean value theorem says that those slopes are going to be equal somewhere between A and B, assuming the function is continuous and differentiable. Differentiable means continuous. So as long as it's differentiable anywhere between A and B, this is going to be true. Here's another example. Maybe I'm thinking about the interval from -2 to 2. So just from here to there. So you got this point here. I don't know what the y value is. It looks like maybe it's like 2-ish or something. And here, got some y value. Looks like maybe it's like -6. Whatever, it doesn't really matter what they are. The point is that if you draw this line between these 2 points, that's somewhere in here, assuming this function is continuous and differentiable, which it is, you're going to have tangent lines that are the same slope as that line there. These lines are all parallel, that's what it's saying. The point of the second picture is that in the first picture, you can see there's only one place where this happens, where these lines are parallel. You could draw all kinds of tangent lines in here, but you wouldn't get a parallel one except for right there. But here, there's 2 parallel slopes. One, I don't know, at this x value, and one at that x value. It doesn't matter what they are, but the point is that there's 2 of them. Nope. One right here, and one right there. So there's these 2 places where these tangent lines are parallel to the one that's in between the ends. So the mean value theorem says. And so we're gonna be asked to prove this. They're gonna give us a function and they're gonna give us an interval. We basically we're gonna write the slope between the endpoints first. Then we're gonna take the derivative of f and see where those things are equal. And those answers, I said where those things are equal. I mean, what x's make them equal? Those x's are the answers to the problem. So for example, it says, determine whether the mean value theorem can be applied to the function on a given interval. So here's a function and here's an interval. They want us to check and make sure you can actually use it. If it can, find a point C satisfying the mean value theorem. So it's like basically, if it can be used, find the X where it actually happens. So if we look at the rules, the prerequisites, it says if f of x is continuous on the closed interval and differentiable on the open interval, we're pretty much going to be worried about whether it's differentiable on the open interval. So I don't really care about the endpoints, though I know it works at the endpoints. This function is actually not differentiable at one place, and that this function doesn't exist when x is -2. So I don't know, f of x is continuous and differentiable for all x that are not equal to -2, because -2 makes the bottom of this 0. And since -2 is not in my interval, I'm good, right? This is from 1 to 4, and -2 is outside that interval, so I don't really care about it for this question. So I am good. It can be, mean value theorem can be applied. And now it says use it, show that it's true. So for these, it's good if you want to get kind of a step-by-step process. First, figure out what this f of b minus f of a over b minus a is, because that's just a number. And then take the derivative and set them equal and find x. So we're going to do the first step, which is to find f of b minus f of a over b minus a. So this is b, and that's a. So I do f of 4. I'll do it right here. F of 4 minus f of 1 over 4 minus 1. This is like I said, this is like this, the right-hand side of this expression. So f of 4 means I put a 4 in here. I get 4 over 6, which is 2/3. Minus, I put a 1 in here. I get 1 over 3, which is 1/3. And the bottom of this is 4 minus 1, which is 3. 2/3 minus 1/3 is 1/3. 1/3 divided by 3 is 1/9. So now I know that the right-hand side of this expression, the mean value theorem wants me to think about, is 1/9. And it says that the derivative says, so basically you set f prime of x equal to 1/9 and then find x. And after we do that, we're going to have to check that it's in the interval. Check that it's in 1, 4. And the mean value theorem guarantees that there is going to be an x between here so that this is true. So now it's time for some calculus. We're going to take the derivative here. This is a quotient, so I must use the quotient rule. So f prime of x is, derivative of the top is 1 times the bottom. That's x plus 2. Minus derivative of the bottom, which is 1 times the top. So that's x. And then the bottom is g of x, the bottom squared. Let's see, x minus x on top is 0. So I get 2 over x plus 2 squared. And the claim is that if I set that equal to 1/9, oops, not negative 1/9. If I set that equal to 1/9 and solve for x, I'll get the answer that they're looking for. So let's see, if I'm just looking at this, I'm kind of forgetting about that part. I could do 2 times 9 equals 1 times x plus 2 squared. So that's 18 equals x plus 2 squared. That's like I did like a cross multiplying situation there. And then maybe I'll take the square root of both sides and maybe flip it around so I have the x's on the left because I like that better. It's not necessary, but I kind of like doing it. So I take the square root of this, I get x plus 2. Square root of 18 is plus or minus root 18. Now I subtract 2 from both sides and I get x equals -2 plus or minus. 18 is 3 square roots of 2. Now I got to think for a minute about my interval. My interval was from 1 to 4. And this is 2 answers. But like, if I do -2 minus a number, I'm not going to get between 1 and 4. I can't. If I do -2 minus something, I'm going to get even smaller than -2. And -2 is already too small. So really what I want is the positive one, -2 plus 3 root 2. And you may not know what this is, but it's got to be between 1 and 4 because the mean value theorem promises that it will be. If I punch in my calculator, -2 plus 3 root 2, I get something about 2.426, 2.2426, blah, 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 a bunch of other stuff. So this is in my interval between 1 and 4, and it says find a point C satisfying the mean value theorem. This is the answer. This is a value of x so that the slope of the tangent line to the curve there is the same as the slope between the two endpoints. So it's basically like, it looks like this. The slope between the endpoints is the same as the slope at the point I found. That's the mean value theorem. That's how you do it. Just to recap, I think the smart play is to do this first, figure out what that f of b minus f of a over b minus a is equal to. Then take the derivative of f, then set it equal to whatever this number was. Remember this number here goes right there. And then, I don't know if step 3 is set it equal and then solve for x, but the last step is to solve for x and make sure that the ones you get is actually in the interval that you want. That's how we do this. Everything beyond this is just like more of the same. So I'll do a couple more examples, and I want to talk about Rolle's theorem in a minute. So it says determine whether the mean value theorem can be applied to this function on this interval. If it is, then find all values of C such that, and this is again, this is the mean value theorem. The mean value theorem says if you can apply it on this interval, then you're going to be able to find a value. You might be able to find more than one. It says all values. It means if there's more than one, they want to know both or 3 or however many there are. So, so like I said, it's a good idea to do f of b. Actually, this is kind of an annoying way to write this. I'm going to rewrite this as x cubed minus x squared, x cubed minus x squared minus 2x. I can multiply this x in here, and it's just, it's going to be easier to take derivatives of this thing. So I'm just going to write it like that. So the first thing I want to do is find f of b minus f of a over b minus a. That's going to be that's like what this part is. So my a and my b are -1 and 1. So if I plug a 1 in here, I get 1 minus 1 at 0 minus 2 is -2. -2 on top. If I plug a -1 in, -1 cubed is -1 minus 1, that's -2. And then plus 2. That's 0 on the bottom. -1. Oh, I see. Sorry. It's -1 minus -1. No, it's -1 minus 1. Oh, it's -1 minus 1 plus 2. Okay, right. So, -1 minus 1 plus 2, that's 0. Well, that's too bad, because that's an undefined slope, and that's not, I can't really do that. Oh, I'm dumb. I was doing f of b and f of a. Sorry. So this is f of a. Okay, sorry, I just about lost my mind there. Let's just try that again. So it's -2 minus 0 on top. And then b minus a is 1 minus -1, which is 2. So this is -1. Okay, that makes more sense. Feel a little better about that. So now this is what the derivative is going to, I'm going to set the derivative equal to this, but the second step is to take the derivative. So I get 3x squared minus 2x minus 2. And then I set that thing equal to -1. That might be the third step right there already. But maybe the second step is to take the derivative and set it equal. But let's just say that. Then we solve this thing. So I get 3x squared minus, I should say 2x. 3x squared minus 2x minus 2 equals -1. I'm going to add 1 to both sides because that's how we solve quadratic equations. Then I should probably factor if I want to get actual values of x out of here. So 3x and x have to go there and there. See, I need a -1 and a +1 to get -1. So maybe the minus here and the plus there. It seems like it would work. See, 3x squared plus x minus, yeah, that works. So this yields 2 answers for x, -1/3 and +1. And I can use -1/3 because it's clearly in this interval, right? It's bigger than -1, but less than 1. So -1/3 works, but this 1 I can't use because it's on the endpoint. You don't get to use the endpoints here. That's why you see how it says on A, B, the parentheses mean it's like open. We don't care about -1 and 1, so I'm not going to use that. So the answer is just x equals -1/3. That's the only place where this is true. And if you graph this thing and look between -1 and 1, you'd see that there was like some kind of a curve, and the place where the tangent line is parallel to the line you draw between these endpoints is at x equals -1/3. So again, same process. We like find this f of b minus f of a over b minus a. We find the slope of this. I would call this a secant slope. You find the secant line slope, take the derivative and you set them equal, solve this thing for x, and then pick the x's that are actually in the interval they were talking about as your answers. Here's another one, same idea. They write it a little differently for some reason, but it says verify it. So my endpoints, my interval are 1 and 9, and the function is root x. So f of b minus f of a over b minus a is equal to, let's see, f of, so this is b, so f of b is 3 minus the square root of 1 is 1. 9 minus 1 on the bottom, b minus a, and that's 2 over 8, which is 1/4. So I take the derivative. This was like my first step, right? Second step is to take the derivative. Derivative of root x is 1 over 2 root x. And now I'm going to set this equal to 1/4. So let's say 1 over 2 root x is equal to 1/4. That means if you cross multiply or just think about it, you get 4 equals 2 root x. So divide both sides by 2, you get root x equals 2. Square both sides, you got x equals 4. And I check that is in my interval, so I'm good. And I say you check that it is and you're good, but like it's gonna be. The mean value theorem guarantees that there's gonna be an answer to this, and it happens to be 4 here. And this square root of x equals 2 only has one answer, so this is the only place where it happens. All right, I'm gonna break this right now, come back and we'll do this, the rest of it in just a sec.